Okay, let's start up in a minute. Okay, let's begin. So I'm going to walk you through this code a little bit. It's pretty basic what it's doing. It's really just plotting stuff and updating an equation that we'll see on the board in a second. We'll repeat this example with the normal distribution, hopefully by the end of today, so that we get a look and a feel. All of these problems are a bit different, and the properties of the parameters are different, and the nature of the priors will be different as well. So I'm going to be telling you lots of stuff, and then later on I'm going to be filling in all the details on it. So right now you're getting the feel of everything, but I want you to look out for the differences and think about the nature of the parameters that we're studying. This parameter lives between 0 and 1, and it has a hard boundary there at 0 and 1. So it's bounded. It's very different from other parameters that we might see. When we see a normal distribution, the mean is unbounded. It lives between negative infinity and infinity. The variance lives between 0 and infinity. So, and it's bounded hard at 0. The nature of the mean in a normal distribution is a shift parameter. It shifts the distribution around. The nature of the variance is a scale parameter. It's actually sigma. It's the square root of the variance. So the standard deviation is the scale parameter. And it rescales the distribution. It changes its diffusion. So those parameters are very different from this parameter. And so I'm going to be talking a lot about properties of parameters. They're going to help us to think about which priors and why. Right now we've just kind of discussed what a conjugate prior is. So a conjugate prior has the property that if the posterior and the prior both live in the same family of distributions, then the prior is called conjugate. You can't tell what the conjugate prior is until you either look at the sampling distribution or the likelihood. It's the same formula, but of course the nature of the formula is different. So in terms of a sampling distribution, it's a distribution on some of the xi's. I've kind of gone back and forth between Bernoulli's and binomial, and so I'll just stick with the binomial. As you notice, the likelihood function is the same for both of them, and that's where all the action is. So it doesn't matter. Sometimes you can save time in problems by recognizing I could use another distribution and get rid of that product or something like that. This was fairly trivial. So the conjugate prior for this problem is beta. So if I make this our prior distribution, we can see with just a little bit of algebra that the prior will be beta and the posterior will also be beta. This would be a really hard exercise to do if you didn't know what a beta distribution is. So half of this class is to be learning the distributions and what their properties are. So I understand that in probability class, they kind of threw a few at you and said solve some problems, work out some expectations, and they didn't fill in all the gaps as to why a distribution is important and why you use it. We'll be trying to fill in those gaps throughout this class. Hopefully you have foundational skills, what a variance is, what covariance matrices are, you know, what expectations are, so on and so forth. Okay, so this is our prior that we're going to use. So our posterior distribution is just going to be the likelihood function, and where do I go for that? I look at the sampling distribution. So if I can write down the process that describes what's generating the data, I've got the likelihood function. I just have to think about it differently, plug in the data, and take all the unknown parameters and let those be variables. And so this exact same function will be here. So I could write it down explicitly the same. P to the sum of the xi's, 1 minus p to the n minus sum of the xi's. And again, all I'm doing is I'm now thinking about this as a fixed variable, something that's fixed in the equation, it's conditioned on. And so this x it's really coming through the sum of the xi's. So I could denote this as it has all the x's in there, or I could say, I'm just going to discuss some of the xi's. It's the same thing. It has the same information about p, because they have the same likelihood functions. So I multiply by my prior. So this is the beta function inverse. P times alpha minus 1, 1 minus P times beta minus 1. And I can take all this stuff that doesn't depend on P and just kind of throw it away. I'm wasting time by writing it down. I'm not actually going to solve the integral down below. The integral itself is a beta function. And typically you can't write those down. So I can write it down in terms of an operator notation through an integration, but I can't explicitly give you an analytic form. So we're not even going to try. So this thing is proportional to, that's our new symbol. I can multiply by any positive constant, and it's expressing the same information. So this will be P times sum of the xi's plus alpha minus 1. So this contribution right here was from the prior, and this contribution was from the likelihood. So there's this trade-off between the prior and the likelihood. 1 minus P n minus sum of the xi's plus beta minus 1. So this is my posterior distribution that is unnormalized. I could normalize it all by dividing by integral P sum of the xi's plus alpha minus 1, 1 minus P, n minus sum of the xi's plus beta minus 1 dp. This is a definite integral, is between 0 and 1. But again, I can't write that thing down. I cannot solve that equation for arbitrary alpha and beta. I would agree if alpha and beta are integers, some of you will know factorial representation of this and be able to express that number explicitly. In general, if alpha and beta are just variables, there's no closed form analytic solution. So what I mean by an analytic solution is an algebraic representation. You could code that thing in. You don't need to express an operator. You don't have to do anything to it to get the formula. So, can't write this. I can write down the idea. It's the thing that normalizes it. So all we really need to do is think about this, though. What's in the numerator? And I recognize this is, that is a beta density function. And its parameters are here. So usually I call that beta tilde, alpha tilde. So I started with an alpha and a beta. Those are my hyperparameters. Let me just write that down. Hyperparameters. Somebody finally got something right in naming something. At least it sounds cool. So you could call them the parameters that underlie your prior distribution. And I bet if you say hyperparameter, people will let you slide. So you should always ask people when they pick these, how'd you pick them? Why did you pick them? And if their answer isn't very compelling, you might want to ask, how sensitive is your analysis to that choice? And in some cases, your analysis is very sensitive to the choice, and you would be weary about trying to convince somebody with that. And in some cases, they're not that sensitive. What we can see is there's kind of a linear relationship between alpha and sum of the xi's. So you can see already where the alpha and the beta pop up. They pop up right next to the data. So as I get more and more data, n increases, it kind of swamps out what alpha and beta are. And so that's kind of a nice property. So if your priors are placing mass everywhere where there's a possible answer, your likelihood will eventually take over the analysis, and most of your analysis should be driven by the likelihood. Of course, there's issues with boundary effects and things like that where you might want to use something to constrain the problem. In Bayes land, we call that a prior. So it doesn't have to necessarily express some belief you had before about the analysis walking in. So later on, we'll talk about that. I'm not saying that's the wrong thing to do. What I am saying is that when you explain it to people like that the first time, it's not very compelling. So people don't like subjectivity, although it's everywhere. So it's a word game. Anyway, I like this name, hyperparameters. So in a conjugate analysis, we're just updating the parameters in the distribution. And so you can already see, in terms of sequentially getting data, this might be very useful. And so your posterior today becomes your prior tomorrow. I'll tell you about sequential analysis later. Okay, so our expectation for this right here, our expectation for beta, or for p, so our prior expectation is equal to alpha over alpha plus beta. Our posterior expectation is updated, given the data, and it's alpha tilde over alpha tilde plus beta tilde. So same forms. If I know properties of my prior, I know the properties of my posterior, because they're the same, they live in the same distributional family. Let me just write down what this is. In our case, alpha tilde is sum of the xi's plus alpha. And then the denominator, alpha tilde plus beta tilde, is sum of the xi's plus alpha plus n minus sum of the xi's plus beta. And so this becomes sum of the xi's plus alpha over n plus alpha plus beta. So that's the Bayesian answer to what they think p is. It looks a heck of a lot like the arithmetic mean. So except there's these little quantities in here. They changed that a little bit. As n gets really big, that sum will get big, and that thing will get big, and this thing will asymptote into the arithmetic mean. And so what the Bayesian is saying is, they like the arithmetic mean as an answer, but that's when n is large. And if you've ever taken a Stat 101 class, they might have taught you to do this analysis using the Central Limit Theorem. And it would impose a normal distribution on this space that lives between 0 and 1, which might not be great. So it could give you an answer that's outside of your range. So what would you do in that case? I guess you go running off and become a Bayesian. So because this answer is constrained to be between 0 and 1 always. So we don't apply the Central Limit Theorem directly. And again, the Central Limit Theorem works when n is big. Quick question, how big does n need to be before you use the CLT? It depends. Yeah, it totally depends. So that 30-31 thing is a terrible answer. So we shouldn't do this to undergrads and tell them the wrong thing. 30-31 would work pretty good if p was around 0.5. But if p were close to the boundaries, it's terrible. So if I wanted to estimate correctly and p was within 1% of the boundary, so it's 0.01 or 0.99 or bigger, so less than 0.01 or bigger than 0.99, to get accurate interval assessments of what's going on, you need like 10,000 samples. So I'll have you explore this later on. So some of you will be repeating an exercise, and later on we'll be doing the Bayesian version of this. Okay, so the answer at least seems sensible from a lot of viewpoints. The only thing we notice is that alpha and beta probably should be small. So what I want to do is I want to explore the code that I've written and kind of change the impact of alpha and beta so you can see what's going on in all of this. So here's my code. Can somebody grab the lights? I'd like this one to show up. I think we can take them all. Do I have control? Well, maybe I have control. Cool. You've got control. Okay, so here's my code. And basically, all it's going to do is it's just going to be running through and updating this equation. Every time I see a 1 or a 0, I change the sum of the xi's. That's the only thing that changes. N changes as well. And so I'm just computing this posterior, and I'm not doing anything too fancy here. So I could have encoded the actual formula myself. It's easy enough to do, and I can write a function for it. But MATLAB also has this function built in, and it's the Beta-PDF. And so I'm using that. So my code, sequential binomial Bayes, takes in 4 inputs: P, alpha, beta, and the number of iterations the number of times I want to flip the coin. So there's a little bit of annotation in here. So I clear my figure, things like that. I title everything. There's some number of iterations in here, vals. That's the number of spots I partition everything. So I'm just taking my space and chopping it up. So I don't actually plot a continuum. Does anybody know why? Because it's impossible. There's no such thing as a continuum. They don't exist. They don't exist in reality either. It might shock you, but they don't exist. It's a nice concept because we don't always like to take limits and we like to use calculus. So I just make this really refined, at least to the human eye. That's all I'm doing. And all I'm doing is I'm taking the Beta-PDF and I'm chopping it up over these values right here. So these are numbers that live between 0 and 1. So they're like 0.01, 0.02, 0.03. That's what these param values are. I shove them into the Beta-PDF function, and I tell it its parameters alpha and beta. And it gives me back the prior. This is the slowest way you could do this in MATLAB, is doing it in a for loop. You can do it all in one fell swoop. So if I handed this the vector, it would give me the vector out. And it would end up using a multi-core system to do that. It would be much faster. So all the code I'll show to you, I'll write in a way like a naive C programmer so that we can all follow it. So I don't ever execute in the example code special MATLAB things that you might not know about. Okay, so I change my axes, I get my prior, and I plot it. I also plot the truth. So the truth is P, and I plot that as well, and you can see how I do that. That's only being used in that one place so we can see where the truth is. The truth is also being used to generate the data, so the data is random. Every time we run this code, it'll run a little bit different. And then I just kind of cycle through the number of times I want to flip the coin. So for I goes from 1 to whatever number of iterations. I have this pause statement in here, and we'll take out that pause statement in a second. I just do it so that we can sequentially walk through, and I have control, and I hit the space bar as well. So I take a draw from a binomial. This is n in the binomial, so this is just one coin flip. So the draw is either going to be a 1 or a 0, and I print that out to you. You can see it go through. And the way to make that happen automatically in MATLAB is just suppress the semicolon at the end, and it'll output to the screen. This is one of the things you can do to slow down your code the very most. So it's a good thing to do when you're prototyping something, but when you're actually executing your code at scale, don't print to the screen. So I/O is very costly. Anyway, I end up doing something similar down here where I update the likelihood. I actually encode the likelihood myself. It's just that formula that we wrote down. So I've got my param values raised to the observed number of iterations, 1 minus P, raised to the n minus the observed. And the observed is changing all the time. I normalize the likelihood, and the only reason I do this is because even though it has no meaning, it's so that you can see it on the screen and it just doesn't climb off the top of the screen and squash everything down. So I do it just for scaling purposes. I will tell you that not all likelihoods are normalizable. This one is. So if you want an example, take a Poisson, observe one observation from the Poisson, say it's a 0, and look at that likelihood function. Even though there's one parameter in the Poisson, the likelihood is not integratable. So it's not a random variable. So I do the same thing for the posterior and the prior, that I just plug that in to the Beta-PDF and I update those values. And then I plot everything. Everything else is just plotting. So let's pick some values. Anybody have any favorite values that they want to pick for alpha and beta? I think some people have thought maybe the uniform was a good idea. Keep in mind the uniform's not conjugate, it's still beta, because I get back another beta that's different from the uniform. It's not uniform anymore. That would be a pretty terrible analysis. My inference is uniform about everything. You see data, it's still uniform. I haven't changed anything. So uniforms don't make good conjugate priors then. It means that you wouldn't observe anything in your likelihood. There'd be no shape to it. So we could use the uniform. Let me just flip the coin a bunch of times. So here's our prior distribution. It's uniform between 0 and 1, and our true answer is 0.7. So same thing as before. I'm going to flip the coin once. I saw a 0, and so the likelihood is 1 minus p. That's a straight line. So what we've really learned in this is this goes down to 0 right here at 1. 1 minus p, evaluate that at 1, that's 0. So the density value is 0 there, and it's only 0 in that one place, except outside of the 0 to 1 interval. And so we've learned it can't be 1 because I just saw a tail, a 0. So we learned something about it. And so this is our expression of likelihood. If I multiply it against the uniform prior, it's exactly the same thing. So it's constant everywhere. There's no shape to that. It's flat. So the likelihood is the posterior because I used a quote unquote flat prior. So there's my likelihood and posterior again. The likelihood is the posterior because I'm multiplying essentially by 1. I keep doing that. And as I see more and more 1s, my distributional assumption, my distribution is changing. I'm updating this distribution. And so this starts to seem compelling. There's a lot of shape to this. It doesn't look like it's a normal distribution. It looks like it's highly skewed. It's telling you that it doesn't think it's 0, it doesn't think it's 1, but it's saying that our posterior is telling us that values in this region right here are probably pretty plausible. Probably could be pretty close to 1. And you'll notice that our curve well overlaps the truth. So there's still a lot of uncertainty. We've only flipped the coin a couple times. Flip it again. Again, again, again. And that's actually pretty nice that it's concentrated kind of in the middle. Right there. So let's do it a bunch more times. So I'm going to do it 100 times, and what I'm going to do is I'm going to stop this from pausing. I do pause for a brief moment when I'm illustrating things in class. That gives the figure a chance to buffer, and it will render. Otherwise, it won't update at every step. So, same problem, same prior, boom. Here's our posterior evolving. It's a density function, so it can't exceed 1. The area under the curve integrates to 1. So it's getting peakier and peakier around the truth. And likelihood functions tend to do that, but through Bayes' rule, I can consider this a probability distribution. Notice that our probability distribution in this case is the likelihood. It's a proper distribution. The flat prior is bounded between 0 and 1. That's a proper prior. And so this is the mistake that Fisher was making early in his career, where he was saying, just take the likelihood and treat it as a distribution. Forget about Bayes' theorem. I don't want to talk about a prior. And I understand the human rationale for that. So, and he would have liked this analysis. So I will say, because things are kind of funny around the boundary, Bayesians tend to like a different prior than this uniform prior. And I'll tell you more about where this comes from. I'll give you a mathematical derivation, but I need to give you a few more concepts before I'm prepared to do that. Bayesians often like this half-half prior. We've kind of seen its properties when we look at it. The prior has this U shape. I'm going to come back around to it, I can't do it justice right now why we like that prior, but just think of it as it's doing something to the boundary that's different than in the middle, even though around here it's pretty flat. So it's somehow treating those boundary conditions, and what I said was the CLT doesn't work very well around these boundaries. And so through this penalization, this soft penalization around boundaries, we get slightly better properties. If we constructed intervals out of everything, so if we were constructing 95% intervals out of our posterior distribution, things I'll tell you about later. There's different types of intervals, but if I come up with the highest posterior density intervals, the beta half-half prior has optimal frequentist properties, meaning that I'll cover the truth better than you do if you use some other property or some other method. So if I used the CLT, you end up covering real poorly near the boundaries. The reason the Bayesian gets this is because of that U shape. So I'll tell you more about that later. What I do want to show you is, let's say, if we look at this prior right here, what it's expressing is the prior expectation is alpha over alpha plus beta. So if alpha and beta are the same, our expectation is, I don't know, it's a 50-50 coin. And that in some sense is objective. So if you didn't know anything about it, you probably wouldn't want to bias one side or the other. So I think we could make a strong argument that unless we had subjective information as to the coin's biased, we probably want alpha and beta to be equal to each other, just because of symmetry. But also, if we make alpha and beta really big, we might be putting too much mass near the middle. So let's see what that looks like. So let's let this be 100 and 100. So big values. So what you can see is my prior distribution is the black dotted line. It's very peaky, it doesn't even fit on the screen. Exactly around middle. And our likelihood function is the red dotted stuff. So it's jumping all around the data and covering the truth, but the prior has too much weight. And so we don't want to do that. So we want the priors to be relatively diffused, otherwise we're going to need a lot of data to overwhelm the prior. So those are just a few properties that we can immediately see what is desirable in a Bayesian analysis. What I love about this also, let's go back to more sensible values. If I ended up letting this be a half and a half, and I flip the coin, let's say 200 times, we can notice something interesting. Early in the analysis, this beta density, it doesn't look normal at all. It doesn't look symmetric. And so it works really nicely in small sample sizes. So people like to study big data, high dimensional stuff. So essentially, when you're studying a problem that's super high D, even though you have a lot of features or something like that, how you fill the space is pretty sparse. I think we just ran out of batteries is what happened. I think it's okay because we're about ready for another example. So even in like high dimensional analyses, they kind of act like you have very little data because the space is very sparse. And so Bayesian analyses are very good for small data analyses because they regularize the space and they account for things like sparsity and boundary effects. Okay, I've got control. So things that you can play around with at home. So I would say, have a look at the code. If you want to rewrite it in R, go ahead. So it's not too hard to rewrite. But it's illustrative. It's about like what a Bayesian's doing. So we get some distribution and we're updating its parameters. And that distribution can look and feel very different for different size n. So I'd say Bayesian analyses are well conditioned on what n is. Using something like the CLT, that's not a very good procedure because it really depends on what n is, whether or not you want to use it. So why do we teach that? Because it's the easiest thing to teach, but it's probably not a great thing to do. Any questions about the beta-binomial example? Quick question. Does anybody know what the variance for beta is? So this obviously matters. And thinking about this stuff kind of matters, because you'd want to know how much variability are we putting into our prior. Obviously, we want it to be diffused. I'm just curious if anybody knows what this is.
Alpha beta over alpha plus beta and alpha plus beta plus 1. Alpha plus beta squared.
Between 2 or 3 of you guys know it. That's actually really impressive. So great job on knowing things about your distributions. I will never test you on this, but I would expect you to know this one. So generally, for every distribution we touch, unless otherwise specified, know the expectation and know the variance of that distribution. Know where it is, know where it lives, know what its expectation is at minimum, because that way we can do a sanity check whether or not we like the answers. You can do a sanity check on your homework or on the test, and try to know the variances as well. Make sure that you don't compute something that's negative, for instance. Anyway, I kind of like our answer, but I think in this part of the story, I haven't totally compelled you to use that beta half-half prior. You might still like the uniform prior. And if P was not an extremely small value or extremely big value, essentially we would agree on our analyses. And so the impact of the prior, so long as I didn't concentrate the mass too much, wore off very quickly. And so there are types of priors out there where they want the impact of the prior to wear off as fast as possible as a function of n. Now I have to define a distance measure to talk about that, but there is a class of priors that defines not a true distance, but a divergence measure, the Kullback-Leibler divergence. So in a Kullback-Leibler sense, we might want our priors to wear off as fast as possible. If you don't know what that measure is I just told you about, Kullback-Leibler, feel free to look it up, but I'll tell you about it later. So reference priors are in that class, and the beta half-half is that reference prior. So what I've just told you is there's other good reasons to like beta half-half. So if you thought P was around the middle of everything, and I used beta half-half and used beta 1-1, i.e. uniform, we closely agree. If P was close to the endpoints and we had small n, we might have some differences. All things to think about. Let's move to a new example. New example. I just want to make sure everybody knows what a normal distribution is, so I'm going to tell you a few things about it first. So this isn't Bayesian yet. So normal distributions. We will be working with multivariate normals, multivariate t's, and doing everything in linear algebraic form, but for now we'll just do it univariate. So if I ended up having something, let's call it Z, is normally distributed with parameter mu and sigma. This is the mean. This is the standard deviation. Sigma squared is the variance. It is not uncommon for me to be talking about sigma and to miscall it the variance, or to have the variance and call it the standard deviation. Forgive me. Just take your square root or square in your mind and replace the word correctly. If you give me sigma, I can give you sigma squared. If you give me sigma squared, I can give you sigma. And in fact, oftentimes I work with 1 over the variance, which is called the precision parameter. We'll be seeing that soon. So a normal distribution, we all know, these look like this. Centered at mu, and sigma is a measure of the spread. That distance right there from the middle, that actually identifies the inflection point of everything. So if you're studying calculus for the first time, they might have you do that this distance is that inflection point. So statisticians probably don't know that, usually because you don't use it, and you don't interpret it that way. It has a different interpretation to us. So normal distributions look like that. So this curve is defined by this function. So I'll call it PZ, given mu and sigma. That's going to put the square on it. Sometimes I do that. So if I put the square on it and I leave the square off somewhere, just remember I've given you the same info. So this is 1 over square root 2 pi sigma e to the minus 1/2 x minus mu, oops, this is a z, squared over sigma squared. And I'm going to write this down just a little bit differently. I'm going to write this as z minus mu over sigma squared. Same thing. Usually they'll throw the variance down here, or they'll tuck the variance in there. So it's kind of nice and polite to not put it in two different forms. But what I want to tell you about it is mu is a shift parameter. It's the mean, we're familiar with that, but it shifts everything. So if I had a distribution that looked like this, that was centered at 0, so let's just say that's 1 over square root 2 pi sigma e to the minus 1/2 z minus 0 over sigma squared. So this would be centered at 0. If I change this to some positive number mu, it's going to shift this distribution over to mu. And it's going to preserve its shape. And that's because everywhere we see that parameter, it's right next to the random variable, and it's just shifting it in a linear way. It's very easy to see. So it shifts everything. This, sometimes people will call it a location parameter. It determines the location of the distribution. Sigma is entirely different. This is a scale parameter. So it doesn't change where it's centered. It either makes it wider or narrower. So if I pick smaller values of sigma, it's going to make it peakier and peakier. And so those parameters have very different feels. I'm going to come back around to all of this location and scale distributions and talk about their properties. But I'm going to do it in a more intuitive and less mathematical fashion the first time we talk about it. If you want to see a more mathematical way of talking about it, go to last year's lecture. So I'm going to change things up a little bit, the way I explain what a scale parameter is. Okay. So we know what a normal is. We like normals because why? What's the big deal with them? You hear about them everywhere.
Self-conjugacy? I think that's one. But also central limit theorem.
Central limit theorem. That's it. Yeah. Averages follow normal distributions. That's almost always true, so long as there's a finite variance. If the distribution has a variance to it, i.e. it's finite, it's a number you can write down, then the central limit theorem applies. So when your old third grade teacher said, well, I'm grading you guys on a curve because you guys are normally distributed, I think, they've abused the central limit theorem. The average of the class is normally distributed, individuals are not. So distributions that look wildly unnormal, so long as there's a finite variance, their averages from their samples tend to look more and more normal. They're not precisely normal. They get more and more normal as n goes up. But we use that sometimes. So normal distributions, it's a cool distribution, and I'm sure that when Gauss figured this out, it was astounding. So there's good reason if you wanted to model things on average, normal distribution is your thing. Nowadays, we like to talk about individuals. So we might not always want normal distributions. I'll tell you about stuff like that later in the class. But let's say I had this problem. X, this means it's sampled from some normal distribution. And I'm just going to write this down as P of X, so that's my random variable, given mu and sigma. Now this is pretty unpolite, right here. This is my observation. And this is the random variable. So what I mean is if I draw this curve, it's got a fixed mu and a sigma. It's not a normal distribution until I plug in actual values for that. Otherwise, it's the whole collection embodying the whole family of normal distributions. So this X is this space right here that everything lives on. So that's the random variable. That's the space in which everything lives. So I'm not going to be super polite about this in this class, but a lot of times they'll make this bold or something like that. And then they'll maybe index this. So what I'll usually do is put an index on it. And I'll use the same notation. So for those of you that don't know what random variables are, you're not super rigid in your mathematics, and I'm not. You're welcome. So for the rest of you guys, sorry. So, you know, I understand some people are like, write it correctly like you're writing it for a journal. It's difficult with chalk. Okay, so this value right here, what I mean by sampling it is I'm going to reach into this distribution, and my hand is going to grab values proportional to the height of the curve. So I'm going to grab values here more often than I grab values there. Keep in mind the probability of grabbing any value a priori is 0. So that happened with probability 0 a priori, and it happened. So I reach into here. It's probably unlikely I grab a value over here. It's probably like 95% likely I grab something over here. So, and if I have 1.96 standard deviations away from mu, that's the 95%. So I grab a value. So let's just start with one data point and see what the value of more data is in the trade-off in the priors. In your first homework, I'll have you do this with n data points. And I'll basically show you how to do all this stuff. There will be an issue that arises eventually by using just one data point. That's also why I'm building that into the example. So our likelihood function looks like this. E to the minus 1/2 x1 minus mu over sigma. This whole thing, I'll do it the way you usually see it, squared squared. So my braces are only in the upstairs. Now I need to talk about what I'm talking about the likelihood for, so I need to give you a little bit more. I'm going to say this is known. Just for now. We'll change that in a couple days. So I'm going to say we're only going to try to infer this. Now every Stat 101 class does this to you, where they say sigma's given to you. You know, eventually they take it away and they start working with t distributions. We'll do exactly the same thing, slightly different reasons. So right now that's known, and this is what we want to infer. We want to learn mu. So our whole goal is to form pi mu, given x1, and I'll be extra polite and tell you that you know sigma. Sometimes you'll see people leave that stuff out. You need to look at their equation to see if they marginalized it away and really gotten rid of it, or are they just simplifying their notation and it's conditional on that value. So I'll be polite for the first part of this class and tell you everything that's conditional. And so what we need is we need the likelihood on mu, given x1, sigma, you insist, and I need a prior. And I'm going to do the same thing I did last time and not normalize everything. You can work out the normalization if you know how to integrate things in polar coordinates. This isn't supposed to be a hardcore class in doing integrals. There's a little bit of work to do. So we've got the likelihood function, and the likelihood just involving mu in the data. I can't throw away anything that has the data in it if it has information about mu. So all that action is here. No mu's over here, no mu's in data sticking around over there. So that's all part of my normalizing constant. Now, if I didn't know sigma, and I threw this part away in the equation, I would have just made a huge error. So, because that's part of the likelihood. But right now, since I'm only inferring mu and sigma as a constant, this is just some number. So this is going to look like e to the minus 1/2 x1 minus mu squared over sigma squared. So that's my likelihood, and I still need a prior. So which prior? Anybody want to throw one out? I didn't ask for a specific type of prior, I just said which prior. Normal. Normal's a good answer. Any others? Flat. So this is the discussion I want to have. Flat versus normal. So perfect. So which prior and why? I'm going to write down two possible answers. Answer 1, normal. So I suppose you're going to come up with pi mu, and it's going to have hyperparameters in there, mu naught and sigma naught. So these would be your hypers. So those of you that said normal, I'm going to ask you next time which parameters and why. If somebody else said something, here's a different answer. And somebody said flat. And this is going to be one of the things you're going to run after first at the very beginning of this class, and later on you'll know when not to touch the flat prior. So I wish I could say flat priors for everything and it all works out and everything's great, but it's not true. So flat. So what's your name? Rosen. So he said flat. So what he means is this. Pi mu is going to be proportional to a constant. So this one looks like this. It's centered around mu naught, and it has some diffusion. It's related to sigma naught. But the flat prior is going to look flat across the whole continuum. There's all kinds of issues here. Is that a probability distribution, for one? And the answer is it's not. So let's come back next time and clarify that. But if we did pick this constant, I'll pick my favorite constant and just multiply it by 1 right here. And what that would mean is that I could recognize instantaneously what the posterior is. It's going to look like a posterior distribution on mu, and it's going to be centered at x1. So if I did just pick the flat prior, if you do normalize this, you'll come up with the 1 over square root 2 pi times sigma out in front of this. We can walk through all those steps next time. But you would get a posterior distribution that a lot of people have used before. And probably in your Stat 101 class, you even thought about your inferences using confidence intervals, maybe thinking about this, and your teacher would say, don't think about it that way. So if you did use 1, I know what the posterior is. It's a normal centered at x1 with variance sigma squared. So the calculation is exceedingly easy. So if I use a flat prior, I'm using the likelihood as my posterior. Fisher liked that. He will not like, at least in his 30s, the argument I'm about to give then maybe you should use a limit of these. And you can form it, rationale that through a limit of this prior, which is the conjugate prior, we'll see that next time, through a limit, when I take sigma out to infinity, sigma naught, it converges to this analysis right here. It also turns out that it's optimal frequentist. And it's what pretty much all classicists are reporting to you. Their answers based off of this, but for different reasons. So they think something different about it, the way they explain it all to you. It's going to take me a little while to get through all of that conversation. So next time, let's come in. Let's work with the normal prior. I'll show you how to compute the posterior distribution. We'll show a limit of it, inducing the flat prior. I'll talk about what that all means. I'll talk about improper priors, and then we'll switch our analysis, and we'll do the same thing where we'll try to infer sigma, given that we know mu. After that, we'll try to infer both of them. So that's it for now, you guys. Also, review sessions are going to be in seats 331, so seats is that building over there. If you know the secret corridor, they do connect, but you can just walk through the aqueduct. That's roughly every 2 weeks. We didn't do a review session yesterday. We're not going to do one next week, but probably in 2 weeks. So just keep that in mind. I'll update the web page so that you can see where it is. Thanks, you guys.